We started out this chapter with the idea of a standing wave. And I should have brought my spring down. I don't have to remember to bring some of these props down. Remember, a standing wave, we could have a wave that was, let's say one hand is here, one hand is here. That's one standing wave I could get. The next standing wave that I could have would be one wavelength, right? And then this would be the opposite, something like that. Next standing wave would be, worst eraser ever, 1.5. So maybe a wave like this. But standing waves come in fixed amounts, right? So it's like I can either have a half, a whole, 1.5, 2, 2.5, 3, but nothing in between. And so what we could say is the size of a wave, a standing wave, is quantized. It can only have specific quantities. And that's kind of like what we were talking about in the previous stuff we were studying, that electrons can only have quantized amounts of energy. Remember that with Bohr? You're either at energy 1, energy level 1, or at 2, or at 3, but not in between. That's what we observe, right? So we have these standing waves. And when we start to try and figure out what electrons are doing, it's not an easy it's not an easy thing to do, because we're trying to look at something so small. So when you try and look at an electron, okay, if I want to look at an electron, my analogy has always been, it's like me trying to see you in a completely dark room with bowling balls. Right? So imagine McKinney's in this room. I don't know where he is. Can't see him. It's pitch black. But I got glow-in-the-dark bowling balls. So I start chucking them around the room, and I see one go like this, like this, like this. And then I see one go, that's where McKinney was. Not there anymore, but he was there, right? The act of observing him changes him. This is what we're talking about with electrons. Electrons are so small that just merely bouncing light off of them changes what they're doing. It changes their amount of energy. So we can't say what an electron's doing at any given point. If we try and look at it, we change it. So just the act of shining light on it changes it. So people get clever. And they say, okay, well, how about we just say, where are you now, where are you now, where are you now? So if we look at an electron over and over again and mark where it was at a given point in time, who cares where it went after that? But I collect all those points, I get a pretty crazy distribution. But if I narrow on the closest 90%, some of them appear to be in a spherical region, right? And we call that S. It's just an S orbital. Okay? And then we found other ones vibrating in different modes. So what was the next shape we started to see?
Bilobe.
Bilobes. So we found some that were in these bilobe kind of shapes. And what I'll do, I think I'll take some pictures of the models and I'll bring to you. But there's some good pictures in the textbook too for this. So then we get bilobes. Then we get more and more complicated shapes. And people go, I know what I'm looking at. That's a wave function. That electron is behaving like a wave, just like standing waves. Except that's a two-dimensional standing wave. And the waves I'm talking about here with electrons are three-dimensional. So the math is a lot more complicated, but we're not going to do the math. Right? What we're going to do is learn the input numbers that you would put into that equation to get back wave functions that tell us what the electron's doing. So we look at the electron, we say, this is what it's doing. Well, what would be the math equation to describe it? This is the math equation. So we're looking at nature, and we're saying, okay, here's a mathematical model to describe what we see. So we had, 4 quantum numbers. First one's energy level, and that's what this 1, 2, 3, 4, 5, 6, 7 is. Those numbers are energy level. And they go from what to what? To range?
1 to infinity.
1 to infinity. Whole numbers. 1, 2, 3, 4, 5, up to infinity. But as you notice, we're probably not going to go much past 7. But we're not going to go around all the way up to infinity. So the first quantum number, again, these numbers are like, think of them as like address numbers. Address numbers tell us, what side of State Street are we on? How many blocks from State Street are we? What side of the street are we on? And when we have all the correct numbers, we have a house. But like I said before, not every address is used. I grew up at 2823. Next door was 2819, no 2821. They just never did this. City planners never put up a 2821. And you can't just go throw any number in for quantum numbers. They have to be what they can be. If, for instance, energy level, 1 to infinity. The second quantum number is rho. I think it looks like an L. What was its range? Rho could be, Andy?
Negative 1 to 1.
No? Ah,
It's n minus 1.
close. Right?
0 to n minus 1.
0 to n minus 1. So 0 to n minus 1 means if you're at n equal 1, 0 to 1 minus 1, 0 is all you get. And that corresponds to the letter S. So this would like be saying, this 1s is like saying energy level 1n is equal to 1, rho is equal to 0, because S is 0. Then you jump up to the second energy level. So now you have n equals 2. Well, what's rho now? Well, it's 0 to n minus 1, or 0 to 2 minus 1, or 0 and 1. Well, 0 we said is S, sphere. Rho equals 1 is P, bilobe. And then we jump up to the third energy level. Now we get another shape because we got a row of 0, S, a row of 1, P, and a row of D. That would be 2, or 0, 1, 2. Yeah, 2. Yes, sir.
So the numbers on there are just representing the energy level?
The number is the energy level, and that's rho transcribed from a number into the letter. Now keep in mind, these numbers we're talking about, like this would be a 3 for n row of 0. This is what you would put into the math equation.
So what does this have to do with electrons?
This is describing the wave, okay, so that's a good question. I mean, these guys would have had some of this already. So let's see. So like if, when we go look at electrons, and I got a computer program that does this, but I gotta bring a special computer down to do it. And I can do that, that's not hard. If I think of the nucleus being here at the center of an XYZ coordinate system, okay? I know that an electron is going to be doing something around that nucleus. And if we look at it multiple times, the lowest energy electron, like 1s, what I find out is if I say, where are you now, 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 I start to get this picture that looks kind of like a sphere. These are just all individual impacts. And if I draw a circle around the 90% closest, that's where the electron's most likely to be, 90% of the time, right? But when we look at other electrons that are more energetic, say a 2p, well, a 2p may be taking on a pattern and this is from reality. This is from actually looking at where electrons were, and then maybe there's some over there. So if I look at the 90% closest of a more energetic electron, it might take a pattern like this. And if it has a pattern like this, that's what we call a bilobe or a P.
So are electrons always going to have like a pattern, or is there
They have a probability of being in that space 90% of the time.
but there's not going to be a chance where they're all scattered and there's no 90%? Like,
Well, 10% of the time they can be anywhere in the universe. Isn't that crazy? So basically what we can say is this. This is kind of what we're getting at, is that where you're likely to find a particular electron is based on statistics. We can't say where it is all the time. We can only talk about probabilities. And so whenever we say an S, sphere, we're talking about something that's vibrating in the simplest mode. So think about it like this. Say I take my spring and I start vibrating it like this, and then I start spinning it like this. You follow me? I start to carve out a sphere. So this thing is acting like a vibration. It's just a complicated one in 3 dimensions. This one, I wish I had my string because it makes it much clearer, doesn't it? I'm vibrating like this, and if I start spinning that, I get a center part that doesn't move, and I get 2 lobes here.
so what the one on the right is?
This would be an S orbital, and this would be a P sub Y orbital. It's lying on the Y axis. And I could have multiple P's. I could have P's on the Z, I could have P's on the Z, I could have P's on the Y. So that's what I'm saying. We're just going to take a while to get caught up on this too. But for now, because there's so much, all that XYZ stuff that's a whole other bundle of worms there. So for now, what I would say is,
So are the P and the S defined by density or like
no, shape.
shape?
Shape, yeah. And now if I have, like the difference between a 1s and a 2s, a 2s is bigger. A 3s is bigger, a 4s is bigger. They're just all spheres. All P's are going to be bilobes, like a figure 8, yeah. but three-dimensional.
And they just increase the number as well.
Yep, as they go up here, you're getting bigger and bigger size. D's are more complicated, that's all I say in the notes is more complicated. Most of the D's take on kind of a cloverleaf pattern. So again, a more crazier vibration. But again, this is based on what we see in reality. And I think it'll help too is, I'll take a bunch of pictures of the models today when we come down to model. Yes. Okay. All right, so those are our first two quantum numbers. N and rho. M sub rho is orientation, right? M sub rho is orientation. So we said that there's really only one way to orient a sphere at the center of an XYZ coordinate system is basically to plop it there. So for S, we just get a spherical shape. And then 2S would be bigger, 3S would be bigger, 4S would be bigger. But for P, start out at n equals 2, because you don't get P until n equals 2. There's no P at n equals 1. If we start at P equals n equals 2, P corresponds to a row of 1. M sub rho is orientation. What are the possible answers for orientation? Somebody said it already in the wrong place. Plus or not plus or minus 1/2.
Negative rho to positive rho.
Negative rho to positive rho. So again, if this is n equals 2, again rho equals 1 here, then M sub rho is -1, 0, or 1. So we could say that this represents -1, this represents 0, this represents 1, because we have these don't necessarily correspond to that letter, but it's close enough. We have a P on the x-axis, we have a P on the y-axis, and we have a P on the z-axis. Px, Py, Pz. So those are your three orbitals. Now when you get up to D, what's rho for D? Rho. S, E. S is a row of 0. E is a row of 1.
0 to 2. 2.
So 2, okay, so this is 2. Then if D is 2, how many M sub rows are there?
5.
5. And their values are?
-2, 2, 0, and 1 and 2.
Negative 0, -2, -1, 0, 1, and 2. And instead of having 3 shapes here for that, we would have 5 shapes. And these would be like cloverleaf, 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 all in different orientations. And then there's that one goofy one that I said looks like a donut with a glazed donut going through it.
That'd be -2, -1, 0, 1.
-2, -1, 0, 1, and 2. Yep.
And that would just increase as the number got bigger.
As the number got bigger, you get more. And so basically we developed this pattern where we have this, is there's, at 1s, there's one spherical shape. At 2s, there's one spherical shape that's bigger. At 3s, there's one spherical shape that's bigger. At 2p, we have P sub x, P sub y, P sub z. And that's -1, 0, 1. This would have the same thing but bigger, same thing but bigger. When we get to D's, now we have n equals 3, rho equals 2, 5 orientations, -2, -1, 0, 1, and 2. We're not going to make you learn those subscripts, but they're things like D sub xy, D sub yz, D sub z squared. Again, they're just explaining where they are in relationship to the planes. Yep.
Is there any reason why it's like why the S, P, and D have?
I don't know why they picked those letters, but it's easier to. I think it's personally easier when you're learning quantum numbers to have this SPD stuff because there's so many numbers going around. You know what I mean? That they're all just 1s and 2s and 3s, and having some uniqueness in rho kind of helps a little bit.
So, if you have -1, 0, 1, are you always going to have, say if it goes up to -2, are you going to have the reciprocal of 2 always?
They're maximums. Okay, so think about it like this. My gas tank has a maximum capacity, 19 gallons. Okay, doesn't mean there's 19 gallons in there. All right, these are maximum capacity. So if this was say 2px, 2py, 2pz, okay, I could have up to 3 orbitals. How many electrons fit in an orbital? 2. Okay, up to 2. And we're going to get that to the last quantum number in a second. So I could have an electron just in this one. Or I could have an electron here and here. and not have this one. Or I could have an electron here, here, and here. Or I could have 2 here, 1 here, 1 here. But eventually they fill up. Once they fill up, you move to the next one. So that's what this order thing is about. This thing fills up, there's only one shape, holds 2 electrons. Then this thing fills up. It's one shape, only holds 2 electrons. Then this thing fills up, but it can hold up to 3 orbitals or 6 electrons. This can hold up to 10, because there's five of those orbitals.
But it can be partially full too.
Partially full, yeah.
And is that the furthest you can go?
No. F is, so F would be row of 3, okay? Whatever this is, that's N. F, row of 3, so orientations, 7 of them. -3, -2, -1, 0, 1, 2, 3. All right? This goes on for infinity, but this is as far as we're probably gonna ever need to go. The next one after it would be 5G. Sometimes we come against that, but this just continues to go on for infinity, which we're not gonna deal with that. Those are all what we call excited states. Okay, then you have the last quantum number is spin. And what are possible values for spin? Plus or minus 1/2. And so that's for each of the 2 electrons. So 1 electron spinning this way, remember that creates torque. When I have a second electron in the orbital, they cancel each other out, right? They don't add torque, as we were showing you earlier. Okay, so that's a pretty good review, but I'm sure you're still like, whatever, Mark, whatever you're talking about.
I have one more question.
Go ahead.
If 1s fills up,
Yes.
do you automatically go to 2s?
Yeah.
Or does it just matter varying?
Yep, then you go to 2s. And in fact, that's exactly what we're doing today here. Okay, so here we go. All right, so the problem that we got here is that, like, trying to describe how this atom is put together, it gets to be messy. Because if I really wanted to draw this out, let's say I have an atom, all right? And let's say it has at least 2 electrons. Well, then we can fill up 1s. And let's say I have more than 2 electrons. Yep. So let's say I have 3 or 4 electrons. Well, then I have to start filling up 2s. That fills next. And then I start filling up my p's. So I start filling up my piece of x, my piece of y, my piece of z. So that's at the second energy level. Then I go to the third energy level. There's my 3s. And here go my 3 p's. And then I start filling in 3 Ds. So there's my first D, my first clover leaf, and I already got a cluster you know what here. I can't tell what's going on anymore. It's just getting crazy. But again, you can see the wave-like kind of behavior of it. So what we've done is we've come up with a way to do a notation to show this a little more easily. We call it electron configuration. So this is the electron. Oops. Electron configuration. Okay, and I'm going to warn you right now. You will find out. Okay, we're going to do electron configuration longhand and shorthand. Abbreviated way to show you how to do it, a long blown out way to do it. And if you look at your periodic table, they actually show you the abbreviated form right on the periodic table. So if I were to ask you, what's the shorthand electron configuration for blah? Some of you guys might go, okay, I'm just going to copy it right off of there because that's the right answer, which is true, it is the right answer. That's not what I'm going to ask you for on the test, right? What I'm going to ask you for is the predicted electron configuration. Because there's about 10% of the atoms that don't follow the prediction. If you want to take AP and understand why, then take AP. But about 10% of the atoms do not follow the prediction for a variety of reasons. I'm going to ask those problems on the test. So if you just try and read off your periodic table, you're getting it wrong. I'm going to tell you that right now. You clear on that?
Yep.
This is a way for me to test that you know the process, okay? And again, you can always just look it up. All right, so this is a way to describe, a way to depict, the shells and subshells. So shells is like energy level. And subshells. Subshells is like, say, 2p would be a subshell. So that would be all of the p's, px, py, pz. 3d would be a subshell, all of the d's, d, 3d, different d's.
Is there where you can, with the window,
What's that?
still be sending me these?
They're there for you, yeah. You should be able to link. If not, you might just have, it might be a login issue.
Okay.
Let me know if you can't, but I do have you on the share. Yeah, you should still be in there. Okay. Occupied by electrons. Yeah, we've been making these all along. You probably get to it a little bit later, but basically my goal is right now for you to jump in feet first, see what goes on, and then if you're getting into it, then we're going to keep you on some current material. We'll worry about the backlog later, because the backlog kind of stuff is stuff that you can handle a lot easier than this. Okay, so let's say example would be copper. Copper. So copper has 29 electrons if you go to your periodic table. Now first I'm just going to show you one and then I'll give you a couple pointers here. So what I'm going to do is first write down the first orbital to fill. And I'm using my orbital filling diagram over there, chutes and ladders. And you see that one S fills first, right? So 1 stands for N, S stands for rho. And I'm going to put a 2 up there. So what I'm saying is this. This is not exponents. Okay? Do not think of this like exponents in math class. This is a notation system. And what this is saying is that in the first energy level, in the s orbital, there are 2 electrons. Because an s orbital is one shape that can hold 2 electrons. So I've accounted for 2 of the 29 electrons. What's my orbital diagram tell me fills next?
S.
So which S? 2. 2s. 2s again is just like s, it's just bigger. It can fit 2. So now I've counted for 4 of 29 electrons. Next comes 2p. How many electrons can a p subshell hold? 6. 3 shapes, right? Px, py, pz. So now I just got up to 10. What goes after 2p?
S3.
3s, okay. And s can hold how many? 2. Now I'm up to 12. After 3s,
3D.
3p, 6 again. Now we're up to 18. After 3p. No, not 3d.
4S.
Yeah. So this is where that order starts to get funky, right? It starts jumping around. So 4s, okay, now we're up to 20. What comes after 4s? 3d. Now if I put 10 in there, so I'm following this order right here. It's
Yeah.
screwy, yeah.
I thought that, but why would you just
Yep.
go to 3D?
1, 2s, 2p, 3s, 3p, 4s, 3d. This is like chutes and ladders. You go down the chute and then you reset up at the next one. Okay? So the order starts going, because again, the amount of energy is actually not just energy level, it's also the vibrational load. And an S is a very simple vibration, where when you start getting into those P's and you get into those D's, are more violent vibrations.
So 1S.
So I like to remember 3D, because if I fill up 3D, I'm at 30. So if I have to do an element that's like 45 electrons, I'm going to run up to 3D real fast. I'm going to fill it all in, and then I'll start picking up counting again, instead of going through the tedious counting everything. But so this one, how many electrons do I have left? I'm at 20 at 4s. 9, so I'm going to put in 9. So although the capacity is 10 for D, I only got 9 left. So that would be the predicted electron configuration. And that's slightly different than what you see on the periodic table. I think the periodic table says 4s to the first, 3d to the 10th, I think is what it says. So it's slightly different than the prediction. Okay, so keep in mind that the order of filling
comes from the orbital filling diagram. So that's just a useful tool to help us predict the order in which things fill.
So if you have 30, you're gonna use the same pattern every single time.
Yep.
You're gonna work up to 30 the same way every time. Now this is all electrons in what we call ground state. That's at their lowest energy state they can have. So it's like if I start dropping marbles, it will come, right? The first marbles go to the bottom. But as the marbles fill up the bottom, then they start to stack on top of each other. So that's what we're doing, is we're throwing them into the lowest energy levels and stacking them up. But we gotta keep in mind that that light could hit them and take them to a higher energy level. So we're not talking about those cases right now. We're talking when they're just at their.
We're just using statistics.
Yeah, where they would be. Yeah. Again, so now and I'm gonna put in quotes exponents, because they're really not exponents. These exponents are the number of electrons in each subshell. Are the number of electrons in each subshell. And lastly, each subshell fills completely. Before moving on to the next subshell. All right, so now that's all well and good. That's fine. That's a nice way to show what's going on. But we do have a shorthand for this too. Okay, now the deal is this. You probably know this from probably 8th grade or 9th grade science, or maybe earlier, and we're going to tackle this more lately. But for one thing, you know noble gases don't react, right? And the reason they don't react is because all the subshells in that energy level are full. And so basically the atom's like, I don't want to give up any, and I don't want to get any. What I got is a very stable arrangement. So it turns out that once you start going up to bigger and bigger atoms, and you're counting past them, so we go past helium, we go past neon, we go past argon. Once we got to helium, neon, argon, those are things that are stable that didn't want to react. So really, it's not important to talk about those electrons because they're not going to be involved in chemical reactions. Does that make sense? That core of electrons that are in whatever you would call argon is just not reactive. But any electrons stacked up above it, they may be reactive.
So if we get to 3D and say we have 27,
Yep.
and it's not full, is there a way we can get electrons from some other place?
You could, and that's how you make an ion. Yep. You could get like, add 3 more electrons, get a -3 charge. That's exactly what it would do. So this is a way to describe the electrons beyond the noble gas core. So we've got some down in the center of this atom someplace is an arrangement of electrons that looks like a noble gas because we've already passed it. Okay, so again, I'm going to show you an example, and then we'll give you a couple notes about it. Here's an example. Let's look at copper, which is 29 electrons. Okay, the first thing I'm going to do is I'm going to go to, yep. or 5, yeah, 5S. Yep. Go to the previous noble gas. Notice I didn't say closest, I said previous. Previous means to come before, right? So if I go to the previous noble gas, for copper, it's argon. I think I want to get a ruler down here too. So if I look at copper, which is right here, number 29, if I start counting backwards, because I need previous, 28, 27, 26, 25, 24, 23, 28, eventually I end up at argon, and that's 18. So this counts for 2. This let's say counts for 18 electrons. Okay, I'll just show you the hard way today, and then we'll do the easy way later, because it's the easy way will make more sense when we get our notes tomorrow. The hard way is this. I gotta figure out where I pick up the sequence again, because 1s is full and 2s is, those things are full down low in the atom. So I gotta figure out, well, where do I start counting? Well, I start counting at the 19th electron. That counts for the first 18. There's 2 there. There's 2 more here. That's 4. There's 6 more there. That's 10. There's 2 more there. That's 12. There's 6 more there. That's 18. I start counting again at 4s. So I pick up the sequence at 4s. So 4s would be 4s squared. And then we said we end 3e to the 9th. Okay, so you resume counting at the 19th. Now here's a little trick for those of you guys that are smart. I'll tell you a day ahead of time. Do you see how if I pick a noble gas over there on the right, helium, neon, argon, whatever it is, do you notice that the next element always comes off in the first column on the left? Would be the next element. Like this is 86, there's 87. That's 54, that's 55. The next one always comes right here. Well, I've already told you that this is the S block. So you will always pick up an S. Look at how many rows down the 19th element is. That's K. See K right there? How many rows down is it? 4. You count at 4s. You will always start at an S. So whatever number you got to pick up the sequence at. So let's say I use 36. That's krypton. The 37th element is rubidium. What orbital would I start with, or what subshell? 5s. Or you can go through the headache and go, well, that's 2, and that's 2, and that's 4, or 6, that's 10, and that's 2 more, that's 12, and that's 6 more. You can go through all that if you want. It's a lot easier to do it the other way, isn't it? Okay. So I was going to go over a little homework today, but I think we had a better review, and actually it was good that we reviewed for everybody. Because this stuff's kind of, you know. I'm shooting for a test next Tuesday. And I'll give you a heads up, because I know that probably a lot of your teachers are going to try and hit you up next week.